We started with the basics that included the complete foundation for atmosphere, which was the layers, the pressure, temperature, measuring instruments, and then we went on to your temperature part of it as well. And I think in my slides itself, I'm covering the previous foundation too. So the target audience is again for me more basics right from BSc. People who are coming out or in the final year or the second year also. Please remember, questions have been asked from meteorology in interviews. Interviews we have sat with the students. They were asking a few very basic questions, and this module is going to help you in that. Anyway, any mates candidate who is in the group also can join, and for anyone and everyone as well. Okay, this is what we did in the last module. We looked into adiabatic lapse rates. Then we saw what is foreign wind effect. Then modes of heat transfer in all the three physical states. We saw what is insolation, which is the energy coming from the sun. What is greenhouse effect? I had asked you a small question on that. We'll look into that question as well. What was a season? And then finally, why mountains, any place with high altitudes or places of high latitudes, why they are colder. So these are the topics done last time. So let us continue from this. My aim is to finish off this foundation with today's session. From when I say foundation, it is all basics. So I might be covering complete the basics. That is what everyone needs before you go into any topic of MET. And particularly these three foundation, please remember, BSc students and second mates, I think most needed for you. You are entering some phase. So for you, it is good. So once these videos are posted in YouTube, you can always see them again before you go for your orals, before you go for your exams. It will always help you. Not only there, it will help you in life also. Couple of questions which I had given last time. I had asked you why there's a difference between DLR and SALR. Is there anyone who wants to give it a try? I have the answers in the next few paras, but if anyone wants to dare to try, please try. No. Okay. I'll give you the answer. Please remember the process of condensation. Condensation means change of water vapor into your liquid state. So during that process, always latent heat is given off due to physical change. So this heat, what it does is it heats up the surroundings as well. So what is happening is the actual DLR, which was 10 degrees per kilometer, because of this heat given off as and when the air parcel is moving up above in the atmosphere, it cools, condenses, gives off this heat. So the drop in temperature, which was 10, is not anymore 10. It is lesser, which is 5 degrees per kilometer. This was the reason why there's a difference between DLR and SALR. Is anyone having doubt on this? It's a simple one. Everything is based on the latent heat given off. Is that fine? This was the question I had asked last time. I know it's almost a month since we did Foundation 2. You might have forgotten. Anyway, let us go to the second question. I had asked you, can we use greenhouse effect to our advantage? Can we use it? Although there's negatives also. Your global warming is one of the biggest negative effect of greenhouse gases and greenhouse effect. But what in the positive side, can I use it? Yes, I can use it. If I'm
Yes,
in a
sir.
place, yeah, you some people would know it because maybe
Polar region, sir. Yes, sir.
yeah, you might be living on a high altitude villages or places anywhere in UP, Himachal, anywhere. Simple like your Darjeeling and all those places. Yes, we already discussed the temperature there and the heat obtained from the sun is not as much as your plains and your equatorial regions. So what we do is we try to trap that heat, and we can use it to grow plants and vegetables. So we can do it. It is very common. Even your commercial buildings and home buildings in those areas where you are living in a hill, you're always longing for the sun. Please remember, you can use a lot of glass. You can use your sunroof. Uh, you might be seeing on your roofs that there'll be a small piece of it made up of glass so that the light comes in. You can trap the heat and still use it. So greenhouse phenomena can be used for your advantage. So yes, it is possible. Now let us see what is in for us today. We're going to look what is wind. We'll look at different types of wind, which is geostrophic, gradient, and cyclostrophic. We'll look at a broader picture, which is called the global wind patterns. We'll look into a couple of periodical and local winds also. Finally, we'll just look into what do you mean by gust and squall, because these terms keep coming in the meteorology, and it is coming in normal day-to-day life also. You still say that suddenly a squall came and went off, or you will say that a gust of wind came. So we'll just quickly look into definitions. Let us go to the first topic, which is wind, its causes, and what are the forces involved. If you ask what is wind, simple answer is wind is air in motion. Why it happens, we'll see. Let me give you a clue. This was one of the question for a BSc interview. What is wind? So you should be able to give some decent answer. You can always start with this one sentence, but you can build up a little bit more. Now, the wind motion, what we measure by an instrument called anemometer, is wind parallel to ground. We are not trying to measure wind which is going vertical up. We are trying to measure which is horizontal. So that is important. You are bothered only about the horizontal. You can do estimation also. You can do it by looking at the sea appearance, and this was introduced by Admiral Beaufort. It is called Beaufort Scale. You might come across that in your meteorology in the class, but still I have got a small screenshot which I'll show you. Just a quick picture of a couple of type of wind sensors or anemometers. The left one is the most basic one. Right side, it's divided into two. The direction and the speed is done by just two different objects, one above the other. But the last one, which is something going on in vogue right now, a lot of vessels have this. It is called gill sensor, is one of the patent gill sensors, or it is called ultrasound. There are no moving parts. Please remember there are four sensors, and they're measuring wind just by transmitting ultrasonic waves. All the three of them, or the two of them, whatever you want to call it, the mechanical ones and this electronic ones, they have their own plus and minus. Please remember, everything has got a plus and minus. You will see if you have on board, you can have issues from the both. I'll give you one simple one. On the left side, which is the mechanical, you can have a jam on the bearings which rotate the fan also, as well as the direction also. So that is one of the simplest problem you can experience. But in the gill sensor, you don't have this issue. You have something else. If you have heavy rains, the curtain of that rain blocks the whole transmission, and you don't get any wind. So that is why I've seen in a couple of vessels where I sailed, we used to have a combination. So that means if one goes, I have the other one. It is more accurate. Gill is a little bit more accurate. It does not wander just like what you have in the traditional one. So doesn't matter. You have plus and minus in both of them, but you will see at least one of them in your sea life. So you will come across that. This is a simple picture of Beaufort scale. If you look at the left-hand side, you have some numbers. This is the number which normally we refer. We say force 5, force 6. What it means is it's got a wind speed, which has got a range, and each range will have a mean. So if you don't know the exact value, then you go by the mean. You can call it as a Siemens term also. I'm sorry, Siemens term, where it gives a name for light air, breeze, strong breeze, gale, and all those things. And if you want to know what it can do, the right side last two columns give you what effect it can do at that particular force. So if you see, if you go to maybe 11, wind force 11, it's storm, and you can see it is showing that things are breaking. The house rooftop is breaking, just like maybe what happened to Amphan, so something like that. So this is one of the scales you will regularly use on board. Okay, let us look what are the causes and what forces are involved in a wind. We already saw wind is movement of air, but why is there a movement of air? It is because of difference in atmospheric pressure between two places. That is a prime cause. But this change in pressure is also due to something else, which is the temperature. Now, we will in this module try to correlate the temperature and the pressure part, how it is related on the Earth's surface. Doesn't matter in the water or in the land. So, this difference of pressure is caused by temperature difference. Okay, what does it do? Anything in nature, doesn't matter atmosphere. You can take a water or anything, whatever. It always tries to equalize the pressure. So when you say equalize, there will be always a transfer of air from high to a low. So high is what? Accumulation or excess of air, and low is deficiency of air. That is what is low pressure and high pressure. This is the basic. So anyone asks you a question in orals, you can use these three columns, these three paras, including the simple definition that wind is movement of air. That is it. It's a simple definition. Okay. Now let us quickly look at how different surfaces creates the different pressures. Let us take a hot surface. That surface can be land or sea, doesn't matter. The air which is immediately above for a hot surface will get heated up. We all know by common sense, anything which is hot air or a smoke, whatever, it rises because of density becoming lesser. Now when it rises, as and when it goes up, please remember the pressure it encounters is lesser and lesser in the atmosphere. That means air expands. So what is happening at the surface level is there is a reduction of air. This is what is reduction of air. So it leaves a place with shortage. This creates a drop in pressure. Okay, this is the first one. Hot surface, what does it do? Let us look at the cold surface. So now the third para what I've written is hot surface result in low pressure at surface level. Let us go on cold surface. Now anything cold, please remember they try to come closer. The molecules try to come closer. That means more denser. The more density you will come down, that means you will drop down to the ground level. So what is happening is when you drop down to the ground level, it is called sinking. You will have excess of air, so that means you will end up in a high pressure. So cold surfaces result in high pressure. So these two are one of the most basics before you start off any talking about any pressure system. You when you see a hot land, you can expect low pressure around there, and if you see a cold place, you can expect a high pressure. Okay, these are the basics. So this is the conclusion I'm giving you on the previous all the sentences and paras. Hot surfaces, air rise, it gives low pressure at the surface. The cold air aloft, which is up, it will try to sink, come down, and create high pressure at the surface of the earth. We already saw on previous modules that the normal standard air pressure at the sea level is 1013 millibar. Now, anything more than that is generally, the word generally I have highlighted. Why? Because it is not always, there's something called relativity also. So, generally, it is considered high pressure more than 1013, and any pressure which is less than 1013 is called as low pressure. Now, this is what I said. It is important to realize that pressures are relative to one another also, rather than just sticking on to 1013. A small example, you might find an area adjacent to each other. One is 1030 and another one is 1014. Please remember, by definition, they both are high pressures. But comparatively, relatively, you should realize 1013, 1030 is higher than 1014. So there will surely be movement of air between these two areas. So this is something important you need to understand. It is not absolute alone, it is relative also. Quick picture of whatever we did. You can see on the left hand side, if it is warm air, it is going to rise up, and cold air, it will sink. And these two pictures depict that if you are having a warm air, the molecules are well separated, and if you have cold air, they are very close and dense. And just to show you how the molecules might be there, again, couple of pictures. So in high pressure, you can see the air is sinking, and in the low pressure, the air is rising. The same thing is depicted on the right hand side also. Now, the forces involved. Whenever wind is there, there are two forces. The first one is called your PGF, or pressure gradient force. It is purely because of the difference of pressure between two places horizontally. Okay, just difference of pressure. That was the plain definition. Now, isobars, we already seen what is isobar. If you have close isobars, that means you got a lot of pressure gradient force. That means the wind force which is generated initially is going to be high, and exactly opposite is the reverse. If your isobars are far away, then you might not have enough force. Now, your PGF, please remember, it will always flow from high to low. And it is always perpendicular to the isobars towards the low pressure. This is one of the important points. Wind also moves from high to low only. So let us look at the first force, which is perpendicular to the isobars. Simple picture which can depict you one of the forces only. So I have drawn you plain, straight, parallel isobars to make it easy. So I'm showing you PGF in yellow color, which is directly going from high to low, perpendicular. Please remember, it's perpendicular. Now, can you apply Bayes-Ballett's law in this PGF as wind? Anyone who already knows what is Bayes-Ballett's law, can you take a guess? Can I apply it on this PGF where I'm telling that it is going perpendicular?
Sir, Bayes-Ballet law is something mixing both, sir, Coriolis and gradient force.
Correct. So that means you cannot apply Bayes-Ballett's law right now. So what I'm going to do is, let us look at the second force. Now, the second force is something which is not real, which is apparent. When I say apparent, is virtual. It's not real, but that is caused because of Earth's rotation. Okay. So what happens here? Looking at the way Earth rotates, we all know Earth on a single definition rotates on a easterly direction. But when you look from the North Pole, it does a counterclockwise. Look from the South Pole, clockwise. Now, these two difference of clockwise and counterclockwise give you two different effects. So that is important for you to come in for explanation of Coriolis force. Now, this Coriolis force, which is an apparent force, basically deflects anything which is moving, any object which is moving in relation to the Earth's rotation. And what happens is deflection is not the same. In northern hemisphere, you have a deflection in different direction, and in southern is a different. So they work different ways. So it is not the same. This is what I said. Anything, any object which is moving, which can be wind, missile, or an aeroplane, with respect to Earth, will suffer an apparent deflection, and this is because of Earth's rotation. Now, as we said, you see from North Pole and see from South Pole, it's different. So see what happens. Anything which is in the northern hemisphere and which is moving will get a deflection on its right side of motion. Please remember, it is right side of the motion of that body. And in the southern hemisphere, it gets deflected on the left side. And this right and left difference is because of your counterclockwise and clockwise. I'll show you some pictures which will clarify this. Now, this apparent deflection is called the Coriolis effect. It was explained, so that is why it has been given a name. Now, what does Coriolis force do? Coriolis effect can be termed as a Coriolis force. It is a force in addition to the PGF. We saw PGF acts perpendicular to the isobars, but Coriolis force acts perpendicular to the direction of motion of that object. It can be aeroplane, it can be your wind, it can be anything, it can be a missile, anything. So it is going to act a right angle to the motion of the object, not the isobars. Please remember this one. So right perpendicular on the northern hemisphere and left perpendicular on the southern hemisphere. A quick picture will show you. Before that, I'll tell you a small formula which can be used for Coriolis force. This is not exactly the formula, it's a representation. The formula can be broken up into V as velocity of the wind, W is your angular velocity of the earth, and your sine latitude. So it is very evident, sine 0, Coriolis force is 0. That means equator, it is 0. But sine 90 is maximum, so Coriolis force is maximum at the poles. So this is what you need to remember. One small example for you to understand. I'll try to explain. Please stop me after this if you cannot. Let us look at the first two pictures, that is the top two pictures, left and right. The idea is to throw something or launch a missile or whatever it is from the North Pole. And I'm expecting that on a reception site or the target, which is at the equator and 0 degrees, marked by a red spot. So this was my intention. Now I launch this missile or whatever I want. If nothing happens, you will see that it will travel like this and finally come here to the target. But please remember, Earth is rotating counterclockwise when you look from the North Pole. So what has happened is the missile was launched. By the time the missile reached here, the Earth has rotated easterly. So the target has gone to this side. So what a person flying in this plane or the missile, what it sees is it has seen that it has missed the target and curved apparently right. So that is the reason the target for that missile is on its left. So don't look from your point. You have to see from the point of the missile, wherever the object is being moved. So the missile missed the target. The target went to its left side, and it felt as if I have turned right. So this is what is the explanation given to you. In the northern hemisphere, objects are deflected to the right, and in southern hemisphere, you plot the same thing. You will see that you will feel as if you are deflected to the left. This is the explanation for your Coriolis force. Something again given to you as a missile or whatever you want to call it. If being launched from the equator, it has got the similar effect. Anything which is launched on the northern hemisphere will turn to its right, and on the southern hemisphere to its left. So this you need to remember before you can finally come to the conclusion why things are turning in some way or the other with the wind and all those things, which will come later. So this is what is Coriolis effect. Is there any question till now? Anyone wants to ask any doubts?
No, sir.
Okay. So let me continue on this. Now again, I have given you now two forces. Yellow was PGF already mentioned to you, and green I have added as a Coriolis force. Now PGF I told you is always perpendicular to the isobars, and initially when the wind starts moving, it will go on the yellow path. But the moment the wind picks up some speed, you will start getting a Coriolis force, and that will be perpendicular to the motion of the wind. So they both are perpendicular. Now what happens in the southern hemisphere is exactly opposite. You will have this green color on the left hand side. Okay. Now look at what is happening as a resultant wind. Now PGF was there, Coriolis force was there, two different forces. So I will get a resultant. So this resultant is shown as the black. Now this is what will be finally the motion of the wind. Now this wind motion, moment it takes a resultant, something else happens. If you see in these three sequential pictures, initially the bottom one I have shown you exactly as the previous slide. The moment I got this resultant force, I told you Coriolis is going to be always perpendicular to the motion of the air missile or whatever aeroplane. So what the Coriolis has to do is, again, it has to become perpendicular to this one. Now when I have two forces here, now the PGF is still a force, but finally you are having this as a resultant. Now because of this black resultant wind, you can see that the green Coriolis force has changed direction, which is again perpendicular. This will again result in one more resultant. Now this is what happens continuously till finally a stage is reached when there's a balance between the PGF and the Coriolis force, and finally this resultant wind becomes stable. When it becomes stable, it looks almost parallel to your isobars. This is what is your resultant wind. Now with this phenomena, I'll show you one more picture. I can start using my Bice-Ballard's law. So that means we cannot use Bice-Ballard's law only on the PGF. Now these two pictures on the left and right show me one in the northern and one in the southern hemisphere. So all of you should remember, northern, whatever I'm pushing, it is turning to its right, getting a balance, finally ending up parallel to the isobars, going to the right side, and exactly opposite is happening on the southern hemisphere. I'm going on the left side. This turning matters a lot, which will explain something else in the coming slides, why something turns in a particular direction. This is what is the reason. So let us look at Bice-Ballard's law now. Now Bice-Ballard's law, I'm going back, it says I face the wind in the northern hemisphere. The low pressure is going to be on my right side. So now Bice-Ballard's law is proven. So that means I'm facing this black color in the opposite direction and low pressure is here. Now same thing can be done on this one. In the southern hemisphere, I'm facing the wind. That means I look into this arrow and I can see the low pressure is on my left side. So this is where the Bice-Ballard's law comes into effect. There are small catch points here also. The first two lines is just what I told you. Let us look at what catch points are there and what you need to understand. This wind, what I had shown you, is associated with plain parallel isobars, which is not very often. It is a little bit rare. You get a lot of other isobaric patterns. Now, when this final movement I told you is parallel to the isobars, so your PGF and CF are balanced. Near the equator, the Coriolis force is 0. If Coriolis force is 0, that means you have only your PGF. So if you look near the equator, you might find wind more perpendicular to isobars because there's no geostrophic principle. Now, practically, whatever the possibility I told you in plain parallel isobars is not exactly possible everywhere. There's one more practical problem also. We have not catered for friction. So friction is a very important thing. It also affects, changes something else also. So if you want to look into this particular whole phenomena, you should be high above, somewhere 600 meters above sea level. Then you can see this whole phenomena coming, which is your geostrophic wind. It is not what is actually happening at the surface level. Something else is happening. I'll come to that. Now, surface friction is there. So what the friction will do? Friction is going to reduce the wind speed and it will change the direction also a little bit. Now the speed, what you see somewhere 600 meters above, if you want to know because of the same principle what is happening at surface level, over the land it might be just half of it, and over the sea it might be around 65%, somewhere 2 by thirds compared to the aloft. Now what happens to the direction? It gives a small angle of indraft. So finally the resultant wind is not exactly parallel to the isobars. It has got a small angle of indraft, 10 degrees or 30 degrees, depends on where it is. Now this is what finally ends up, and this blue color what you see is called the actual wind. So this is what is the actual wind. This is not the resultant wind, this is the actual wind. So you will see it with a small angle of indraft, speed reduced. Now you have all the forces coming to picture, PGF, Coriolis force, and the friction which is changing the direction and the speed. So this is what happens. So with result of this, now what will you see in your isobaric patterns? I'll just come to that in the next few slides. Let us look at a geostrophic wind scale. This normally is given to you in the weather facts. When you see a weather facts, you might get this on one top corner. How do you use it? So it's very simple. All I need to do is, let me tell you that, let us take this example on the left hand side as the weather facts I received. Now I plot my approximate position. So vessel is here. This geostrophic wind scale is basically used with a condition that the isobars are at 4 MB intervals. So what I do is I take my divider, around my vessel, I measure the distance between the closest two 4 millibar isobars. I come with the same divider. I know at what latitude I am. Let me say I am at 48 degrees north, or this north, 48 degrees north. So I keep my divider like this. You will see the point of the divider coming at this place. What I do is I come parallel to this graph and I come slowly down and I take off the reading here. So this is what is the geostrophic wind right now. But again, as I told you, geostrophic wind principle works only somewhere around 600 meters above the sea level. So what you need to do is, obviously you are at sea. Please take in 65%, 66% of whatever the measurement you got. So that should be approximately the wind in your area right now. A small point for you to remember, this weather facts would have come after the forecasters analyzed and consolidated and sent to you. By the time you reach, it comes to you, please remember the time has elapsed. So the isobars, what it is shown in the weather facts is not exactly right now. So please give a small allowance. Don't go start arguing and fighting that this is not right. No, it is because the change of time also. So it is one way of seeing how much can be the wind right now. So it is just a method to find out what wind is possible. Now I'm
Sir, we
yeah.
also keep in mind the speed of vessel, sir, because it also affects the wind.
You can find the apparent from the apparent wind. You can find the true wind by using wind triangle. So you will always try to compare it with your actual wind. That means the true wind, not your apparent wind. What you get on your anemometer when you are moving is apparent. But the moment you are stopped or you're an anchor, the anemometer gives you the true wind. That means the real wind. So just remember that you can always convert it and then compare. You should convert it and compare, not your apparent wind. Is that okay?
Yes.
Okay. Now I've shown you this picture again because I'm going to change the isobars to circular or curved isobars. That is more important for us. I told you this plain parallel isobars is a very rare phenomena, and normally you will not see in the surface. It might be high up above. So I should be able to formulate something so that I can deduce it for a curved isobars, which is more common on your surface, on your weather faxes. So let us look and take this concept and move forward. So I'm going to keep the bottom part of it, bottom part of these parallel isobars exactly the same. I'm going to curve the top parts. Now this is what is curved isobars. Now look at the phenomena, what is happening in northern hemisphere on a low. I'm going back again. This is also northern hemisphere, and the low is on the top and the high is on the bottom. You saw that the resultant wind started doing right and parallel. Now I take the same analogy. I curve the isobars. Now see what is happening. This is what is happening in northern hemisphere. Can you see the direction of motion of the wind? It is turning anti-clockwise. Something important for you to remember. Northern hemisphere, winds around a low is anti-clockwise because of this reason. Now let me go to the southern hemisphere. We already saw in the previous picture, in the southern hemisphere, the Coriolis force makes the resultant wind turn left, and finally it is parallel to the left side. Now if I give you a low in southern hemisphere, you can see the wind turning clockwise. Now this is the biggest reason for you to remember that a low in northern hemisphere, winds will turn anti-clockwise, and in southern it will turn clockwise. Now let us look what is gradient wind. Gradient wind is the winds associated with curved isobars, curved and circular isobars. That is what is gradient wind. Now the answer for the last two slides is here. Here, northern hemisphere, low pressure is cyclone, wind moves counterclockwise. High pressure is called anticyclone, wind moves clockwise. This name is confusing, but yes, this is how it is. Uh, the forces in the curved isobars or circular isobars, it is not limited to PGF and Coriolis force. There's one more. Can anyone take a guess? What is the one more? There's one more force involved in a curved isobar. Anything circular trying to move will create some other force.
Cyclotrophic force.
Centrifugal.
Centrifugal, yes. Centrifugal force is the answer. So what you have is you have a centrifugal force that will always move out radially. So if you look at this gradient wind where we have PGF and Coriolis force, you have something else also. Now, in a low, let me just, if you want, I'll quickly go back to a low circular isobars. You will see the PGF, what you see here, was going towards the low pressure. Coriolis force was going outside, and centrifugal force also joins in with it. So finally, the balance is achieved between your PGF and these two. And exactly little bit opposite happens is, if I am talking about a high pressure, this centrifugal force takes the other side. It goes to the other side. That is how it is, because in a high pressure, wind is going from high to low. That means going outside. Centrifugal also will go outside. Not necessary for you to remember so much. It is just a basic. So how the pressures are balanced. Okay. Now I should not forget about the friction. I will have a reduction of speed also, and there will be a in draft. So let us look at the picture. What exactly happens on a closed or a curved isobar? Now you have the green color pressure gradient going in. Your Coriolis force was, yes, exactly opposite. And what is happening is you get one more additional force called centrifugal. And finally, because of the friction, you get this blue color, which is your true wind. Now let me go to the next picture. This is what you will see actually around a low in northern hemisphere. And this is what you will see in the southern hemisphere. Now, can you correlate this one? You will have seen this in those people who have already seen some weather facts. You will have seen this in the low pressure in northern hemisphere. You will have the small arrows being shown slightly tilted towards the low pressure always, and they are moving in counterclockwise or anti-clockwise direction. Southern hemisphere, the same low with the same angle of indraft in clockwise direction. These are the two pictures for your actual wind. Again, one more picture which is showing you all the forces together. So a low pressure, wind is slowly going towards the center. In a high pressure, wind is going away from the center. If you are looking only at the northern hemisphere, low is anti-clockwise direction wind and high is clockwise direction wind. And if you go to southern hemisphere, please do exactly opposite of these two. So if I say southern low, it is going to change. It will become clockwise, and southern high will become anti-clockwise. Easy way to remember is, please stick on to one hemisphere. You can always make it reverse to the other one. And even more easier is northern hemisphere low, it is going to be anti-clockwise. So if you remember just one, you can go on deducing and talking about others. Okay, let us. Okay, I'm trying to give you homework since I have drawn some pictures. Maybe if you want to try this, draw a wind associated with the high pressure in southern hemisphere. That means you'll have to show the breakup of all your PGF, Coriolis force, and your centrifugal, and finally how it's going to turn with a small angle of indraft. You can try this as homework. Although we might not have any more sessions on the foundation, but it is something good for you to learn. You can Google it, you might find answers, but since you know the concept, you can try it here also. It is tricky. I told you, northern hemisphere low pressure, wind circulates anti-clockwise, but it's called cyclone. And high pressure is called anticyclone, but the wind circulates clockwise. So something to remember. Exactly opposite is in southern hemisphere. So I'm not going to stick on to this. It is tricky. Now this is what happens for you in a northern hemisphere. Air spirals inwards towards the center in a low pressure, and in a high pressure, air from top comes down and diverges. So that is why a low pressure is called a place of converging air, and high pressure is called place of diverging air. Again, one more. Uh, One of the important points you need to remember is uh, air or wind. Please remember, it cannot be. It is an energy. It cannot be destroyed or created. It is there. It just changes the forms. So if I have a low somewhere, there will be a high somewhere nearby, adjacent, or a little bit far away, but doesn't matter. So this air which is converging here finally on the top has to fan out, and please remember it has to go to this place and come down. That is how the whole cycle is completed. It is not that suddenly something is getting generated and then destroyed. No. So this is what happens. The low pressure air which is coming up has to go somewhere to some other place and fill up that, give it to that high. So that is how it works. So on a larger basis, when you look at the weather facts, you will see a lot of low, high in alternate spaces. So that is how they find the balance. So this is what actually happens in real life. Okay, there's a small topic called cyclostrophic wind. Uh, Not much data is there, but I have tried to make it very simple. Uh, don't have to remember everything, but the first para is the definition. It is the wind which is found to blow nearly parallel, actually almost parallel, with the circular and crowded isobars. Why? There's a reason why they are nearly parallel. I'll just come down to the next few slides, next few paras. It has a simplified formula calculation for calculation compared to the gradient wind. You don't have to remember the formulas. It is again exactly the same thing. PGF balancing the Coriolis and centrifugal force in a low pressure in northern hemisphere. Now what they have found out is the Coriolis force compared to these other two, the PGF and centrifugal, is very, very low near your tropical region and in a cyclone. So what they do is they discard it, and that is the reason they say that it is nearly parallel. So I'm discarding the Coriolis force. Now, this is a small formula which they use for calculation. This is how they predict. So there's no need for you to remember this, but just to tell you that this is how they predict how to calculate the wind speed near a cyclone. They would have done this maybe in this Amphan cyclone also. They could have used it. Let us go to next topic called global wind pattern, which is more happening all over the globe, with few exceptions. The exceptions are because you don't have a continuous patch of water or continuous patch of land. It breaks. So you might have some deviations, but we'll look only in the general pattern, how this came about. Uh, See, it is very similar to the gradient wind, but on a global scale, the local exceptions, as I told you. Now, we already saw if I have a hot surface, I will generally tend to have a low pressure there and rising air. Cold place, I will have more denser and descending air. So this is what we have seen. Now, the first explanation to global wind pattern came from a person called George Hadley. Uh, he proposed that equator, since it gets always a belt of intense heat, it is going to have a permanent low pressure over it. And then he said that poles are always colder, then it will have a permanent high pressure. So he deduced explanation. He said that this is what happens. That means there is one huge loop of wind which starts from the poles up to the equator. So at the poles, cold air sinks, travels along the surface. At the equator, it rises up and completes the circulation. As I told you, it cannot be destroyed. It has to go and circulate somewhere. It has to go and fill up somewhere. So this is what was explained. But this didn't work out well because we had more loops. There was not a single loop, there were more loops. So what happened was someone else also came. So he proposed that no, we don't have just one loop, we have more loops, more permanent lows and more permanent highs. So that was by someone called Ferrell. He said this is not a single loop, it's going to be more loops. So how he explained is, he said that there is one more high pressure and a low pressure in between these two. So we have seen already the poles and the equator. So he proposed that there is two more permanent belts. So there is one high pressure and there's one more low pressure. Now, when you look at this picture, you will see if I start from the pole, there is a high, there is a low here at 60 degrees, approximately 66. So it is high, low, high, and low. The same thing happens when you come from your southern latitude also. You have a high, then a low, high, and a low. So this is what they found out is actually happening, and the simple one cell, one loop explanation of Hadley was not accepted. So Ferrell gave his own ideas, which was more practical. So that is the reason it was accepted. Now this is what is happening around the surface. Now you can see the first two uh, poles cold, so air is sinking. Equator hot, so air rises. Now these two more permanent belts. Again, I got alternate high, low, high, low. So at low it's rising, at high it is sinking. So what happens because of this is I start getting more loops. Basically, I've got totally three loops. So the first I'm going to explain two loops, then I'll come to the third one. Look at what is happening at the poles. What they say is uh, air, the cold air sinks here, travels along the surface, but comparatively with the poles, by the time it comes to around 66 degrees, it warms up. It is again comparison. It warms up and it rises, and this forms one loop. And very similarly here, the, the warm air rises up here and it goes up, and by the time it reaches here, it becomes cold and it sinks, so it forms one more loop. Now, the effect of these two loops gives us one more loop here, which is a kind of maybe secondary effect of these two loops. So what I can say is this parcel of air here, the air which is adjacent here also will come down, and air adjacent here also will go up, and it forms the third loop. So this is the three loops which we normally find in reality. So that was explained by Ferrell, and since it was making more sense, people accepted it. All the three loops were given names. Uh, Still, Hadley was the first man, so his name was still retained on the first loop. Then the second one was called Ferrell cell, and the third is called polar cell or the polar loop. These are the three giant loops which happen on the Earth, and exactly similar. Please remember, happens on the southern hemisphere also. They do a mirror imaging. Now this picture gives you that mirror image as well. So you can see three loops on the northern and three loops on the southern. Again here, there's one small thing you can try to understand. Please remember, wherever air rises from the surface and goes up, it adiabatically cools and gives you a lot of precipitation. So please look at these places. At the equator, I have a lot of precipitation, which is called your tropical region, tropical rainforests. Now I got one more loop here also. There also I will get a lot of precipitation. But look at this in between gaps. These two gaps are known for deserts. Why? Because dry warm air is always coming down, flowing down, so you don't have much of moisture here. So you look at your geography, you will see around this belt you will get a lot of deserts on the northern hemisphere and supposed to be deserts in southern hemisphere. We don't have much of place. So you can take example of Australia, it has got deserts also. So you will see these two places. So this is the reason why a different type of geography is there, which is actually a result of your winds also.
Sir,
Uh, Yeah.
But sir, Sahara Desert is at the tropical region.
It might be
What is
continuing also.
what sir?
No, it might be continuing. It's not just on the tropical region.
Yes, sir, but it also present as tropical regions also.
True,
What is the reason?
true. Please, I cannot give you the exact reason. Maybe some geographical researcher should tell you that. But what we are trying to tell is a generic explanation. You will have a lot of ifs and buts. I told you the whole land and the sea feature are not continuous on the globe, so they break up. So you'll have a lot of freak things also, which is not normal, and I may not be able to explain everything. Yes, when I say you have a desert somewhere around 30 degrees, that doesn't mean the desert is only at 30 degrees. It can come down. In Rajasthan also we have a desert, and that is much maybe less than maybe 20 or something, somewhere around 20s. So it is possible it can extend. So I'm not sure. I cannot give you that answer. I'm sorry for that. Maybe I'll try to find out. I should try to find out from some person who is a researcher in geography. Sorry about that. Is that okay?
Yes, sir.
Okay. Now we saw the loops. These loops, what do they do for us in the surface is very important, because that is what creates the global wind patterns. Now we already saw that anything which is moving in the northern hemisphere will turn to its right. Now let me just come make the example explanation a little bit simple. Let me stand at this high pressure. We all know that wind will always move from high pressure to low. That means wind will go from high to low here, and wind will go from high to low here. So what is happening is, any wind which is going in this direction will take a right. Any the wind which is going in this direction also will take a right. Let us look at this one. The wind sinks. You got high pressure. That high pressure also will go towards the low pressure. It will take a right. Now, wind is always mentioned from the direction which is coming from. So, if you look at it, this is an easterly wind. This is also an easterly wind, but this is a westerly wind. Do you all agree with that? Wind is always coming from. I've given a curved path so that I can mention the Coriolis effect also. So it is always coming from. So what you have is two easterlies and one westerly. Exactly same thing, mirror images on the southern hemisphere. Now look at the names what they give. On the polar side, on both the poles, it is called polar easterlies. Polar easterlies. And near the equator, this is called northeast, because it has got a direction. So it's still easterlies, northeasterly trade wind, and I've got southeasterly trade winds. Now these two are both westerlies. The name given to this on the northern hemisphere is called prevailing westerlies, and in the southern it is called roaring 40s. The name it has been given because everything happens around that 40-degree south latitude. That is the name given. So this is your global wind pattern, which affects and matters a lot. Please remember, all your depressions, all your low pressures get affected by these wind patterns on a global scale. Now, again, I'll show you a couple of pictures which gives you some more hints. And you might have heard something about horse latitudes. You might have heard something called doldrums. So doldrums is somewhere your equator.
ITC, sir.
Sorry?
ITC, sir.
ITCZ, yes, Intertropical Convergence Zone. Why? Because it is tropical and two wind patterns are coming and converging, so it is called ITCZ also. Okay. Now, horse latitudes, why it was called? Because the early sailing days, this small band. I'll go back to this picture again. The small band, you will see there is not much of air in these bands, the gaps. So what happened was, sailing vessels used to get stuck, and anyway, when ration pani is going down, you have to sacrifice something. So the easiest was, before throwing the man out, they used to throw the horses out on the water. so that they can reduce the weight, less food, less water so that they need not spend the food and water for them, save it for the men. So that is why it was called horse latitudes. It was called only in the northern side. Why? Because mainly the trade was done in northern hemisphere from Europe to US and Caribbeans. So that is why it is called there. But phenomena is exactly the same. Some of the pictures shows here also, but not much of clue is here. But there's a lot of history around the northern latitudes. So these are again the same names, the cycles, all of them here. I'll just quickly show you a couple of them. Okay, I'm done with this global wind pattern. Let us quickly go.
Rajesh, can I take 30 seconds of your time? I'll just launch the polling.
Sure.
Okay.
Yeah.
Yeah. Thank you, gentlemen. Thanks for the polling. Okay, Rajesh.
Thank you. And I can see one person is given good, not excellent. Not I'm not trying to ask what it is, but if there is any improvement, please give us some ideas where we can improve. So only for that, not because of the, not because of trying to garner any results. I'm not going on that. Please share us. In the last, I'll be giving you the email also. If somebody is new, please share the feedback so that we can improve on it. I'm almost done. It is not much for me. Couple of more slides, and I know we have already shot by 5 minutes now. Let me quickly do this remaining part of the winds, which you need to know. Something to do with the local and periodical. Periodical means it is doing cycles. That means regularly it is happening. We already saw that warm air rises and cold air sinks. So over the land, if you see in the summer, it gets very hot. So you might get low pressure there. And this generates something called sea breeze. Now, if you are in a coastal state like Chennai, you will see this sea breeze is very active somewhere in the afternoon when the temperature goes up. It starts off a little bit before afternoon, but peaks up late. So what is happening is it is because of the difference in pressures. The land is at a low pressure. The sea compared to this land nearby is at high pressure. So there is a movement of air between this sea and land. So you get sea breeze. It helps us a lot to keep the coastal states temperature under control. Otherwise, it will be very hot. So sea breeze helps us a lot. That is the reason a lot of people go to the beach to enjoy the sea breeze. You would have seen always it is hitting your face. It is not hitting your back if you face the water. So that is the sea breeze. Now, opposite happens in the night time, or it can be winter also. The same land, please remember, can give off heat very fast. So it can become colder than the water in the night time. So you get a reverse effect. You will get a land breeze. That means wind going from the land to the sea. This usually happens late in the night. And normally, I know nobody's sitting at that time in the beach. So you might not have seen. So you will always see the sea breeze. A couple of pictures which will support this concept. Hot land, air rises, and I got high pressure here and low pressure here. This cycle completes, and I start getting this sea breeze when I go to the beach. Now, exactly opposite happens in the night time. You can see the land becomes very cold, so it attains a relatively higher pressure, and a low pressure is on the water. So you will get the opposite cycle happening at early in the morning. You will not see this before. That it will be only in the early in the morning when the temperature drops drastically. So this is what is called land and sea breeze, which is local and periodical. There is one more set of local winds, which is called katabatic and anabatic wind. One of them is important for us. The second one is not so important. And let me just quickly talk about the katabatic with a small diagram also. Now, katabatic means a downward movement of a parcel of cold air from the land on a clear night. So what happens is it uses more of gravitational force on the land slope. By the time it reaches the surface of water, that means just the beach, it might reach storm force depending on how much speed it has achieved by the time it came. It is a danger for shipping. If you are somewhere in the places where this phenomena is common, and if you are doing any cargo operation, early morning you should be careful, because a lot of instance when it has broken the mooring lines, might damage your hoses in case you are in a tanker. So you have to be careful. Katabatic is important for a mariner. The opposite is anabatic, where the wind is going up above in the slope, which is not of any particular significance for seafarer, but both of them are there. I'll quickly show you the picture. This is what is your katabatic and anabatic. Anabatic, I'm not bothered much. Katabatic, yes, on a cool, clear night, near a very steep, slopy port, if I'm in a harbor, you should be careful. Check with your shore people if these phenomena occur. Then you will have to take extra precautions, or think about it, whether to continue on the cargo or not. Now, the last slide. We'll just quickly talk about the gust and squall. I told you you will come across this. Gust is basically a sudden increase of wind speed for a very short duration. It will be just coming as a peak for a few seconds. If you have a digital recorder on an anemometer, you can record the peak velocity. So you will see that it just comes and goes off within a second. Now, what is a squall? Squall is a broader concept. It is not a few seconds. It lasts for a few minutes, where the whole mean wind speed rises. That means you will see for a couple of minutes the wind speed has gone up. It is not for a few seconds, it's for a couple of minutes. But you can experience this last line. A squall may include many gusts. So this is something you can experience. So this is the definition of your squall and gusts. I'm going to give you a couple of minutes for questions, and I'm going to conclude. I'm done with this module. If you have any questions, do ask. Then I will conclude with my standard signature slide. So you will see that. Any questions?
Sir, in one of the previous slide, you show that resultant wind force will be 2 by 3 above the sea surface.
Yeah.
And 1 by 3 only in the above. It will be opposite, no, sir, because friction will be there above the sea.
No, I'll tell you something. On the land, the friction is more because of obstructions. On the sea, the friction is lesser compared to the land. That is why if you take a geostrophic wind scale and measure with your divider, because of your isobars, you will get a geostrophic wind speed. What do you do with that? If you are at sea, you will take 66% of whatever the answer you got in the sea. But if you are in land, which is not for a mariner, if someone is interested standing at home and he still wants to use a geostrophic wind scale, what he will do is he will divide it by 2, make it 50%. Obviously, because of trees, buildings, and whatever landscape, there will be a more reduction than the sea. So sea will be at higher comparatively when you look into land and sea. Is that okay?
Okay, sir.
Any more questions? No. Okay. I know all of you are tired today, Saturday, and want to go. Let me finish off with my signature slide. Now, I've been telling right from the day one on the module one, I said that meteorology is nothing, is not a subject, it's something which you live. So I'm going to ask you, did I talk anything about man-made in these 3 modules? I think no. But if you look at other subjects, they're all man-made. So what we have discussed in the last 3 modules is what is happening in nature without you interfering also. Everything happens. So that is the reason I call nature is meteorology. Please don't take met as a subject. It is something where you are living in. So I stick on to this last equation. It's always there. Maybe that is the reason my interest is much more than a lot of other people. So don't take it as a boring subject. Uh, Please start using small happenings in nature every day. You will learn a lot of things. You will try to figure, and you will make more justice. You will start loving it rather than mugging as a subject. That is my final parting words. Uh, the references I used was Captain Subra Marine Meteorology. I've used even the HMSO Met Office book and some details and the pictures from the internet.